share We are still waiting for about 10 people. So let's start in maybe 10 minutes. As you can see from the background change, I'm teaching from the university now. Hopefully we can have class in offline soon, but with the current department policies, some of the class has to be taken online, or some are able to, we are able to have them offline. For the master level, it depends on the preference actually, because the department opened up with, later on actually, whether we want to have this online and offline. But I already had the discussion with the head of the department back then, and we decided to make this offline. So that's why we still here. Good thing is that you don't have to travel as well. Some of you, especially students who are still here, well, you still have to be here, I suppose. Okay. There are still a number of you guys that haven't submit the second assignment. It's quite slow. What happened? Do you still hear the sound echoing right now? If that is the case, all right. What happened here? Let me try to turn this off. It might be due to the what has happened? Maybe I need to clear it from. Let's see. Switching the microphone. This is because of the microphone. Do you still hear the echo? Is it because of the room, or is it like echoing in? Maybe I should hear it myself. Let me. Let me try to join with the phone. See if I can hear my own. Testing. There's no echo. All right. Okay. Don't think it's because of the of this bill, because this is from connecting to the phone. Yeah, probably because of usually I would let it kind of correct itself, but somehow maybe because the program cannot react fast enough. I am using the notebook to run this right now, and it has to record to do the screen recording to using the camera at the same time recording the screen using Zoom and playing our audio program as well. So it seems like cannot catch up with that. Okay. Right. So what I'm trying to find out now is how come there are some of you who have not submitted the assignments today. This already this is the submission days already. Right. Or maybe, well, one possible explanation would be that a lot of you have already withdrawn from my class. Yeah, that might be it. Who knows? No, there are actually still 20 of you guys. So, oh, did I? So 10 of you have already submitted, but about half of the class have not done that yet. Please do that soon, so that I can grade your work here, and also the first one as well. I haven't graded the first one. Oh, but there are review pending, and 20 of them. Or did you have you already submitted all of that? Maybe so. Somehow the system showed that 9 hasn't submitted, but 20 has already done that. So I think it should be fine. Don't know what happened. Okay. For today's content, we will still not have the assignment, the next assignment yet, because next one will be on convolutional neural network. This lecture is still not that point yet. So we should begin. It shouldn't take long for today's lecture, but it is one of the important topics and quite hot research in deep learning. In fact, if you compare to other aspects of deep learning, you will see that the aspects that is least developed would be the one about optimization of the deep learning model. But this is quite strange, right? Because when you talk about when you mention the name deep learning, since it has the name learning, it should relate to the learning algorithm. But a lot of the work that has been developed so far focus on the architecture of the deep learning model. Only a few have been kind of focusing on the algorithm, the learning algorithm itself. Many of those still based on gradient-based learning. One of the reasons is because gradient-based learning is faster than the other approach that relies on the stochastic properties to explore the parameters. But who knows? Maybe when you look forward for the next say 5 to 10 years, the optimization of deep learning might be different from what we have today. So let's start. What we are going to look at today is the algorithm, right? The algorithm to update the parameters. You have already seen last time that if we have the network architecture, we can use gradient to update parameters in order to make the parameters reflect more to the data, to the pair of input and output, so that you have a model that are able to map from input to output. So that is how the model learn patterns in the data. But there are different ways to update parameters, and you may have seen in your implementation of stochastic gradient descent that if you set the learning rate to be too small, what will happen would be that it will take too long time. It will take a long time to optimize parameters. The parameter will be approached very slowly. If you set the weight to be steep, if you set the weight to be high, then it is possible that the parameter optimization could jump across the optimum solution, and it create a type of jagged parameters optimization pattern that it kind of going around instead of just approaching the target. And that would again take the model longer time to optimize for parameters. So what we are going to take a look today are a bunch of algorithms, a bunch of ways that allow you to optimize, allow you to update the parameters in more intuitive sense. More specifically, we will take a look at the optimization of the training of the parameters in the deep learning model. The thing that we will take a look at today would be covered in the optimizers of Keras. If you use Keras, you have to specify the optimizer in the compile method. Right? Before you fit the data with the model, you need to compile the model. In the model compilation, you can specify, for example, the loss function that you want to use. You can specify the optimizer that you want to use. You want to use it to optimize the model. This, for example, in the code below here, you can see that the above here is the model specification using the sequential method. Down below here, in the one of the parameter of the compile, you need to specify optimizers. And here I specify it as SGD. SGD is an object here, an instance of the optimizer.sgd, the capital SGD. That you can specify learning rate, decay rate, momentum, and other parameters like Nesterov parameters. But what are they? We are going to take a look at those today on the meaning of these parameters and the significance in terms of the optimization. Okay, now let's take a look at the usual step in optimization. Right? When you initialize the optimizer, when you compile the model, you can either specify to use to instantiate the optimizer and then use those instance, pass that instance to the compile method. or you can specify it by name. The difference would be that if you use the name, it will use the default parameters. But if you use the instance, like this, you use an instance like this, you can specify specific parameters and then make an adjustment on the optimization itself. Okay, so there are lots of choice of the optimizer to choose from, and some of them have certain similarities and have certain characteristics when you choose to use them. Let's take a look on what they are and then try to understand more. That will make you able to make the informed decision on the architecture of the optimizers that you want to apply to your model. Okay, so there's a bunch of choice like the stochastic gradient descent, the SGD. There is the Nesterov momentum, AdaGrad, AdaDELTA, RMS prop, Adam, Nesterov, Adam. What are they? Let's take a look. Before that, let's switch to the official Keras sites, and you see that here there are a number of optimizer available. I'm not talking about the new one here, FTRL, but we will talk about all of this. SGD, RMS pop, Adam, AdaDELTA, AdaGrad, AdaMax. I'm not sure if we are covering this, but let's see. NEDAM, and you can see the terms that are related to this, like ADA usually stand for adaptive, and N is Nesterov. You see later what are the meanings of these terms and what are the significance in terms of the optimizers. Right. So first of all, this particular lecture is, although we are talking about optimizers and these relate to the codes, but this lecture requires no coding at all. We are going to take a look at the mathematical detail on how an algorithmic detail of these things, so that you would understand why the optimization behave in a certain way when you use this specific choice. Let's start with SGD. You have already implemented stochastic gradient descent, so I will go over this very quickly. Okay, stochastic gradient descent is an algorithm that you can think of it as a gradient descent of a subset of data. That subset of data are sampled stochastically from the whole dataset. So in order to do so, we require to have first the learning rate that you want and initial parameters. And in stochastic gradient descent, we will the algorithm will stop when you have a certain criteria met. For example, maximum iterations, the constant gradient, increase in error. So there are a bunch of criteria that can be specified here. And in each iteration, these are the things that will need to be done. First, the algorithm will sample a mini batch of m examples from the corpus, from the data set. So you will have the training sets x1 to xm, right? So for each iterations, mini batch will be sampled. And these x will be associated with the corresponding target that you want to predict. Afterward, the algorithm will compute the gradient, G. Gradient is computed from the mean of the gradient, the same thing that we did in in backpropagation, right? So it will be the derivative of the loss function. Okay. Once we get the gradient, the parameter theta will be updated based on the gradient. Okay, it will go in the opposite direction of the gradient. And then this will be repeated a number of times. All right, so this is the way that the stochastic gradient descent work. It uses stochastic here, the sampling, to avoid stuck at the local optimum, because the stochasticity of the process would allow the exploration part of the optimization. Okay, before we begin further, let me draw this two words. The first one is exploration, but I just write O. Got distracted, sorry. Should have a command like talking and then it draw it for me. Exploration. Sorry, but I think you can guess right. I didn't bring my pen with me. Here, the first is exploration and another is exploitation. Exploration and exploitation. And optimization need to consider both. Optimization. Right. The optimization has to consider both aspects. In different optimization algorithm, it will contain different amount of exploration and exploitation. For example, I think the best example would be the search algorithm. You can think of a search algorithm like the branch and bound or the technique like A star as a heuristic algorithm that you find the solution if you have the same configuration, same input, same output, you get the same solution, right? That is more if you consider these two aspects, you see that that type of algorithm would exploit the solution, would try to find the best solution so far. The technique like gradient descent and least square is an exploitation base, that it doesn't allow any randomness in the solution. However, it is often found that when you are too greedy, you stuck at the local optimum. Okay, if you just want to go down and then you go all the way down, or if you want, say you want to earn money, then you think that okay, education is not necessary. Let's go find some money. You get stuck at the local optimum someday, and that is exploitation. Exploitation would take the value at hand as first priority. However, it is often stuck with the local optimum, and that make it not very useful in the long run in order to find the global optimum or the better solution. So the optimization usually need to incorporate another aspect into it, which is the exploration. The exploration aspects of optimization would try to explore for a better solution, a better forms of answers. I think the best example of this would be the genetic algorithm. I'm not sure if you have learned that yet. Genetic algorithm encode the solution as the bit string, and then it try to combine them together through the crossover and through the mutation of the solution in order to find a new generation that has a better fit to the problems. That is actually the exploration part of this optimization. The ability to randomly mutate the solution to get to the better solution, that is the exploration part of this. And think about, well, in order to get to the point that you want, maybe you need some exploration, right? Not just to study hard, right? You need to kind of relax and then going randomly sometime. And I think that a good example would be your thesis. When you do your thesis, if you just start with one topic without any exploration of all the topics, you just get stuck at this topic. And when you graduate, you learn only that one topic. But with certain exploration to the different stuff, you will expose to different content, and then hopefully that will shift you toward the optimum goal that you want to go. I don't know if that is a good enough example though. But yeah, in these aspects, optimization needs to contain both. You need to have a certain ability to explore the answer, to go randomly to the solution space. But you need to still maintain the exploitation that you want to go to the general direction that you want. Right? Both will be combined together. For the stochastic gradient descent, exploitation part is in the gradient update. That is, in every gradient update, you need to go into the direction that is opposite side of the gradient. For the exploration for the gradient descent is encoded in terms of the sampling of the mini batch. So each iteration in in the while loop here, you have chance to sample to pass off the data so that you can update to that part alone, and that would create a types of like an ensemble model like in random forest that you can get to reduce the variance in the data that your model exposed to. Okay, so this is the essence of stochastic gradient descent in terms of its nature in optimization algorithm. Okay, any question about this one? You have already implemented this, so it should be easy for you guys now. Okay, let's move on to the next one. Now, what is the problem with stochastic gradient descent? Stochastic gradient descent without momentum would be like this. Like you can bounce around and get to the solution quite slowly, right? Because it kind of changed without regard to the previous change. They have, well, I would say, people in researcher in the fields have invented with the technique to use a type of smoothing technique, or think about like driving a car to include the momentum of change into the gradient update as well. So rather than using the gradient, if you take a look at this equation, the right hand side here is the gradient, right? The gradient of the current batch that you want to update. But rather than using it to update parameters directly, you use it to add that to the previous change. So that means this change will be added to the previous change, which still have the alpha here to control the parts that you want to use from the previous gradient. This is momentum. Okay, that means you use instead of using the instantaneous gradient to update that, you use that instantaneous gradient to update the to update this one, and this will work as a smoothing function that take in the previous value and then update this value so that, well, you will update the change a bit and then shift the direction according to the gradient, and this would control the shifting in the direction rather than the overall movement. And then the whole new here will be used to update theta. Okay, this is the stochastic gradient descent with momentum. It will change to the solution faster because you have the momentum value to kind of control the change such that it would not go zigzag like this one, right? So this is the momentum. Oops, I got questions. Oh, okay. Sorry, but you still have time until midnight. I just want to remind you, you have not upload your solution yet. Please do so. All right. All right. So the momentum allow the gradient to be more stable. So rather than switching gradient, well, just think about it. When you want to go down the hill, you don't have to evaluate the direction every step on the way. You can just evaluate the direction in order to shift the direction of movement, and that is the momentum. Okay, you can see that. You can see here just modifying optimization a bit. It actually allows you to reach the solution faster here. Okay. Right. So if you combine momentum with stochastic gradient descent, the algorithm will look like this. So we need to have a learning rate, but this learning rate, rather than affecting the solution, affecting the value of parameters directly, this learning rate would affect the momentum. Okay, and then you will have this momentum parameter alpha. If you are familiar with the smoothing technique, this is very similar to exponential smoothing. That is, you would have this smoothing factor. Okay, also alpha. So this is the momentum parameter, but it is the same as smoothing parameters. And then you have initial parameter theta, you have initial velocity v here, and then it would doing the same thing for the while loop until you reach the criterion. Then the algorithm would sample the mini batch with m samples, so you have corresponding x and y, and then you would have the algorithm would compute the gradient, the g here, the gradient, which is from the loss function. So this gradient will be the same as in backpropagation. And then the algorithm STD with momentum, we will compute the velocity update. This velocity update is alpha v and minus epsilon g. That means gradient will be used to update this velocity, and the velocity will be used to update to the parameters. Actually, you view this, you don't have to think about it as velocity. You can think about that as the exponential smoothing. This is essentially the exponential smoothing of the gradient, right? But instead of applying the smoothing technique like that, you kind of apply it online to update, smooth the change so that it wouldn't go too drastic in terms of switching point, a zigzag like that. We take the gradient, take the general direction in mind, and then use that in the update here. Okay, this is SGD with momentum. Let's look at Keras function and see how you can modify these momentum parameters. I'm talking about SGD now. Here's the SGD class that you can initialize. You can see that here we have the learning rate, okay? But you also have momentum. Once you specify momentum, then the SGD will act like what I just told you that, right? But there is another one here, the Nesterov. Here, yeah, you can see here. This is the equation when momentum is 0. So this is just like the one that we have been using so far. And when you specify momentum, then it will be velocity equal momentum times velocity minus learning rate times gradient. Okay, and then the velocity added to weight. Right. For the Nesterov, let's look at the next slide. Any question about momentum first? Why would you want to do that? In order to accelerate the learning process without affecting the step size, without affecting the learning rate. Okay, you would be able to reach to the optimal solution faster than without one. Okay. All right. Since you have already implemented that stochastic gradient descent, implementing momentum is very easy. Just change from updating gradient to just using the velocity to update, and that's it for the momentum update. Now let's take a look at one that is a little bit more complicated. Right? This is introduced by, well, I have a problem pronouncing his name, so Skever. Right? This paper introduced a type of momentum algorithm that is used, inspired by the Nesterov accelerated gradient method, proposed since 1983, right? Before the deep learning eras. And this one is quite good in a lot of sense in terms of updating and getting to a solution faster. Let's take a look how it works. So the update rule for the Nesterov momentum is this is the update rule without Nesterov momentum. So here you have the loss function and take the gradient, updating the momentum, and then use the velocity, updating the velocity, use the velocity to update the parameters. Okay, with the Nesterov momentum, the gradient is evaluated after the current velocity, right? The current velocity is applied. Okay, so what does that mean? Right, Nesterov momentum, the gradient is evaluated after the current velocity is applied to update parameters. So let's take a look at the meaning of Nesterov momentum. This one is a picture that I think is best explain the Nesterov momentum. Okay, so how does it work, right? So we need to first make a big jump to the direction of previously accumulated gradient. That's the concept of momentum. Going this way, and then correction going this way, and correction. This is and then gradient make you correct the path. This is usually the way that you want to go. That the algorithm would go. For the accumulated gradient here, it would take in for the standard momentum. It would go like this one, right? Go up and then go this way. For the Nesterov method, I think maybe let's take a look at this one rather than that. So the idea of Nesterov method is to apply gradient to evaluate gradient after the current velocity. So the difference in terms of algorithm would be that you need to have interim update, right, from using the gradient here. And then after that, after updating this, we will use these new parameters to compute the gradient at the interim point. So instead of using the gradient of the original point, we use the gradient of the new point in that direction. Okay, use the gradient of that new point. And then use this gradient to update the velocity and use the velocity to update the parameters. Now let's sink it in a bit. What does that mean? It means that at this step, you are looking forward and imagine what would happen if you take the same step again. At that point, would the gradient still go that way or the other way? Right? You just use that instead of using the gradient at the current point. It's just like when you look forward and then you guess from the point that you see forward whether you want to go forward or you want to turn or you want to make change of the parameters update. Okay. To explain this further, let me draw a picture here. Let me go back to that picture. Let's say you are in your gradient update, you are updating into this position, and then you are trying to move forward, and your V tell you to go in that way. Then you would use the same parameters. Like this is the last step that you took from this previous point, and then you use the same step, update it again, and this is the new point. And then from this new point, you try to evaluate the gradient of this new point, whether you want to go forward or backward. And then you use the gradient of this new point to update the parameter at this point. just like driving a car and then assessing the situation up ahead, and then use the thing that you perceive up ahead to adjust the course before you go forward. Okay, this is the Nesterov momentum, right? So for this one, okay, let me change this. For this one, this is a jump that you make, and then you see that at this point you need to make this adjustment. So you will use this type of accumulated gradient to make an update instead. This is two jump. Okay, this is standard momentum that we have, two jump. We use this one to update to this direction, and then we then use the next point to make an update again. Okay, so from this algorithm you can see that we need to evaluate the interim point and then use the parameter at the interim point to calculate the gradient again, and then use the gradient at that location rather than the current location, right? So when you compare the usual the normal momentum and gradient descent with the Nesterov momentum, the difference would be only that whether you would use the projection to the gradient of the projected point or the gradient of the current point, right? So in the analogy of going down the hill, it would be that whether you would use the current position or the position that you see down there, right? And the gradient that you perceive down there to make an adjustment of your current location. Okay, this is the Nesterov, and it is quite promising in a lot of modification, especially when you combine this with the adaptive momentum. Okay, so this is the SGD with Nesterov momentum. The SGD with Nesterov momentum can be adjusted here, Nesterov. Just turn it to true. Well, you can see that implementation is quite easy, right? Turn it to true, and then that is the Nesterov momentum. Now let's see in the equation here. In case that if looking at pseudocode is still quite confusing, maybe looking at the actual code here, pseudocode here, will make you understand it easier. Okay, so comparing to the above, here you need to multiply momentum with velocity, update the momentum, update velocity with the gradient and the learning rate, and then add the velocity to the parameters in order to update the parameters with the gradient plus momentum. With Nesterov equal true, then velocity would so you would update. So velocity would still be the same point, but you would update the parameters with the moment time velocity minus learning rate, right? So you update this with actually this is the gradient of the next point. So rather than using just velocity alone, you have to use the momentum as well, and this gradient would be the gradient of the next step, right? Gradient of the parameters after you have already changed that. Okay. Right, so the default is false, but it can be turned into true. Although with the stochastic gradient descent, Nesterov is okay, but there are a better adjustment on the algorithm with Nesterov criteria later on, when you will see that. Okay, and that comes with the adaptive learning algorithm rather than having SGD, because if you take a look at this, you can see that at the beginning, if you use the same step size all the time, it will take quite a long time. Let's say if you want to go like when you drive a car and you want to use Google Map to guide you to the location. If you glance to the map all the time, well, you don't have to do that, right? You need to know just the general direction toward the location, toward the area. and then you can fine-tune the solution, trying to find the exact location later on when you want the finer detail. The same goes for the algorithm or for the optimization of deep learning as well. That is, you don't have to have the fine step at first. You can have a coarser step at the beginning and a finer step at the end. So in that sense, you don't want your learning rate to be static. If your learning rate is constant, that means, well, you want the solution to be highly finer in terms of the step name of the resolution. You don't want to miss the solution. You might need to use the smaller step size. If the step size or learning rate is small, they will take a long time to optimize for that, which is undesirable. You might want the adaptive learning rate. That is the learning rate that change according to the iterations, according to the general landscape. So defining the learning rate has been one of the research focus in deep learning. How to get the right learning rate at the right time. Okay. So if you set the learning rate to be too large, then it might miss the solution. Too small, it would take longer time. Momentum allow you to affect learning rate a bit. Okay, but having momentum means that you need to have another parameters to fine tune. That means you now have both momentum and learning rate, and you need to fine tune between two of them. So there are a number of incremental improvement in optimization algorithm to introduce the adaptive learning rate, the learning rate that can change by its own when further down the optimization. Okay, let's take a look at some of these and the idea behind that. Before we begin, actually, if you take the course in optimization before this course, you might notice a method called simulated annealing. Right, simulated annealing. Simulated annealing. Simulated annealing, or the Gibbs sampler, is a method that allows you to optimize the solution with the stochastic method. Its analogy is an annealing process in metallurgy. So it's like cooling down a hot iron, hot steel. You need a process to anneal to gradually reduce the temperature. Simulated annealing, when you consider it, you see that actually the way that it works is also very similar to the adaptive learning rate concept that we see right now. That means actually a lot of techniques are sharing between computational techniques all across the fields. If you learn technique in optimization, you will find that they are quite similar in terms of the generalization of the concepts to the one that you learn in this course. So my suggestion to you all, the master students and PhD students, would be to study a lot in different aspects in computer engineering, and you will see the essence of each technique encoded in different subjects, and that will enhance your perspective in computing and allow you to be able to adapt techniques from what you learn in pre-auto course to the other course right here. Some of the things I taught you here, I actually learned from the class like digital signal processing, class like discrete mathematics. But in the end, they are kind of combined to the concepts that you see in this course. Okay, all right. Let's see the technique that allow you to change the learning rate accordingly. Okay, the first one is called AdaGrad. AdaGrad would adapt the learning rate by scaling them inversely proportional to the square root of the sum of all historical square value of gradient. Let's take it in a bit. That means at the beginning, it would have the learning rate that is quite large, right? Because it's scaled by the inverse proportion of the size. When you see the square root of sum, it essentially telling you the norm of the historical value of gradient. So if you have a lot of gradient, computed earlier, the step size will be smaller. That means along the road, the gradient, the learning rate would reduce. But initially, the learning rate will be large. So parameters with the larger partial derivative would have the rapid decrease in learning rate, while parameter with small partial derivative would have a small decrease in learning rate. So that means if you have already taken a large step, then your next step will be smaller, and then it would kind of converge down to the solution that you want, right? So let's take a look at the algorithm for AdaGrad. So for AdaGrad, you need to have learning rate, epsilon here, initial parameter, theta, and well, a small constant, delta, very small constant to make comparison to. And we start with the initialization of gradient variable r equals 0. And then for each one, you can see that the essence of stochastic gradient descent is still here. You need to first sample for the mini batch, and then compute the gradient of the current location, right? Of the current location, and then use this gradient to accumulate, right? This is R. Think of R as accumulated gradient, but it is the sum of gradient, so that you have only the size. Yeah, you have only the size of the gradient. So take the square of gradient, take it in, and then we will update the parameters according to the learning rate over square root of R. Okay, delta here indicates that the initial gradient is small, and then this is multiplied with or dot with the gradient itself. Okay, this would be multiplied together with the gradient, and apply the update. Okay, so that means the size of the gradient, this is like element wise multiplication. Okay, so that means the size of the size of learning rate would change according to the size of the accumulated gradient. This is AdaGrad. Ada stands for adaptive learning rate gradient. So this is adaptive gradient. All right. Let's take a look at the AdaGrad in this. This is SGD. Let's back up here. AdaGrad. AdaGrad has the initial specification of learning rate with 0.001, and the initial accumulator value is 0.1 rather than 0. Doesn't affect much. This is just to make sure that there is no error. So this is like a small delta that I'm talking about. And here is also an epsilon. Epsilon is small floating point to avoid zero denominator. Okay, so you can find a reference here in the Lucy 2011 for the AdaGrad algorithm, but they are the same as what I just described. Okay, that means the epsilon here, and this is the delta in my equation, small floating point to avoid zero denominator, and the initial accumulator values. All right, this is the AdaGrad. Let's take a look at another one. I think there will be something happens. Okay, right, there will be animation here, which I will show you later on the performance of each comparing to one another. But you know, there are actually papers that try to compare performance of each of these. It turns out that Some work well in some situations. Um, the meaning that means you need to test which one work for your problems. Okay. Right, but let's understand them first. Okay, this is AdaGrad. Next is AdaDELTA from the paper in 2012 by Siller. AdaDELTA and Adaptive Learning Rate Method. Well, for all of these are available, so I would suggest that if you want to study them more in terms of the inspiration, the test, the results of that I got from those papers, read them, and then maybe if you want to do research in this in the optimization method, this would be a guide for you guys if you want to do optimization with the deep learning. Right, AdaDELTA. Well, what are the different points comparing to AdaGrad? AdaGrad is sensitive to initial condition. For example, if the initial condition take you to the last step, the next step will not be larger than this one, it will be smaller. Okay, so if the initial gradient is large, learning rate will be lower all the time, which sometimes is actually a bad idea. Like if you make mistake in the initial step, that mistake will carry on through the rest of that optimization or mystery optimization, which well should avoid that type of thing. You kind of need to have a little bit more exploration. So AdaDELTA come to help to overcome that sensitivity in the parameter selection at the beginning by introducing the decay of the learning rate. Right. So let's take a look at AdaDELTA. In AdaDELTA introduced another parameters called decay rate. Here, rho as the decay rate. So start with initial parameter. This one I take it from the original paper, so it will look a little bit different from the previous one. Previous one are from the book. If you want to find the reference here, these are from the book. That's why the algorithm has this reference here, and it's quite easier to explain for the book because it has already summarized and has explanation there. But the book doesn't contain AdaDELTA, but Keras has AdaDELTA, so I figured out that I should take them from. I should explain that with reference to the paper here. So let's take a look at the AdaDELTA algorithm. In the AdaDELTA algorithm, it is still an adaptive learning rate. But what does it mean by delta here? This is actually delta in the abbreviation. I don't remember what does that stand for, but let's try to understand this. So you have initial parameters x1, x of iteration 1. Okay. We need to first initialize the accumulation variable, this e of the g square of the gradient equals 0. And so this is just like the AdaGrad. And e of the change in parameters, right? Change in parameters also 0. That means it considers not just the gradient, but also the parameter as well. So for we will do the looping a number of times. First, we need to compute the gradient. When we compute the gradient, then the gradient is added to the accumulated gradient. Okay, this is the old gradient at the previous iteration and the original gradient. The gradient is computed here. This is added to this with the rho as the parameter to specify how much part of the accumulated gradient would take from the previous accumulated gradient and the new one. So again, this one is similar to the exponential smoothing. That is, to taking parts from previous accumulated gradient and another part from the new values. It would act as a smoothing of the accumulated gradient. That's very similar step to the momentum. And then the update is computed, but well, this is quite complicated comparing to the last one. Well, the update is of the delta x here, which will be used to update the parameters downward here, is computed from the RMS function of the of what of the this is the gradient. So this is still the update using the gradient, but the change would be the learning rate, right? The learning rate will be changed from just the value of learning rate. It will be changed to the change in the parameters of the previous step. Compare this RMS is actually the square root of the E, right? To get the norm values out of this. So this is the change in the parameters comparing with the change in the gradient. Okay, now let's stop and think. Change in parameters of the previous step and the change in the gradient of current step. What does that mean? Well, let's imagine the value. Okay, if we remove the top part, if we remove the top part here, you get AdaGrad, right? Accumulated gradient. But as the paper suggested, that AdaGrad is a little there is a downside of AdaGrad. That is, if you take last step at the beginning, then there can be unfortunate updates later on because the last step at the beginning. For example, if you take one last step at the beginning, but there's still a long way to go, you shouldn't reduce the learning rate yet. You should still use that. So this algorithm use that update to indicate whether you still want to have higher learning rate by using the size of change. This is the size of change in the last step. Okay, so this is like a momentum. So if the momentum is still on, you still need to use large learning rate rather than using a small learning rate based on the accumulated gradient alone. So that's why we have the next step here, which accumulate, doing the exponential smoothing of the change of x. So if the change so far is still large, then you still need to take a large step. But if the change in the last step is already small, then the learning rate will be small eventually. Okay, then you use this delta x to update with the xt to get the new iteration of x. Okay, this is the AdaDELTA. Okay, very similar to AdaGrad, except that it has this carry on momentum to include in the calculation of the learning rate. All right, this is AdaDELTA. Let's now switch to Keras. AdaDELTA here. Okay, in the AdaDELTA, you need to specify just like in the AdaGrad. First, the learning rate, and then epsilon. Okay, but there's this parameters rho, which is specifying the decay rate of the previous used previous used gradient. You don't want the gradient to carry over since the beginning. You want to just a few earlier to be used here. So this row would indicate that values, right? So this is AdaDELTA. Well, this is AdaDELTA is a lot more robust comparing to AdaGrad. AdaDELTA. Alright, maybe let's move on. Okay, we have covered 3 of 7, I think. Now let's take a look at the next one. This one was proposed by Hinton in 2012. A modified version of AdaGrad called RMS Prop. he does, well, instead of using the Ada family line, kind of invent a new one called RMS prop. This one perform better in the non-convex setting. Well, it's like in the simple, it perform better in a simpler situation, a non-convex setting. Right? Oh no, it is convex setting similar. So this is performing better in the non-convex solution. The solution that is that might be a little bit more complicated. By instead of going like AdaGrad, this one changed the gradient accumulation with into something like exponentially weight moving average. Now think about that. Because what we have seen in AdaDELTA is actually exponentially weighted as well. You can see the similarity between concepts, right? Even though he has the new idea, this should work to exponentially weight, but it is still very similar to the earlier one. Let's see the difference later on. Okay. So when you apply this with the non-convex function, I will show you what non-convex function means. Seeing a picture might be better. Non-convex Euler plane. This one. This is quite good. Here is an example. This is convex. Convex means that you have one solution. In non-convex, you might have multiple optima, and this creates a problem when you want to optimize parameters. Okay, so it means that this one might be better if you want to optimize for the solution when there are local optimum and global optimum, but you don't want to have something complicated like the stochastic optimization or the stochastic optimization like the ABC, like the genetic algorithm, like that. So the same optimization is still applicable here. Okay, so how does it work? When you apply the non-convex function to train with neural network, learning trajectory, the learning of the parameters might pass through different movement, different structure until it arrives at the local optimum or the locally convex area, the area that you need to optimize. So AdaProp take into account of that and create a part of exploration steps that you can incorporate it into the model. I'll try to compare this one with the AdaGrad, right? And also the AdaDELTA that we mentioned earlier, and you see how it progressed to this point. So, well, you start seeing the similarity. Start with, again, we have learning rate, this epsilon as learning rate. And this is the decay rate, right? Rho. Don't want to say that they are the same thing. They are quite similar. Okay. And you have the initial parameter theta and a small constant delta here that is used to stabilize the division and initialization of accumulation variable R. Okay, and the algorithm starts with sample a mini batch M, well, just like SGD, and then compute the gradient G, and then G will be used to accumulation by taking rho from R, the accumulation, and 1 minus rho from the G square, similar to the previous one, okay, to the AdaDELTA. And then compute the parameter update, the delta theta, as the minus of the epsilon over the square root of delta plus R, then multiply with G. and use this to update the parameter theta. All right, this is IMF prop. What I want to talk about here is IMF prop, although very similar to AdaDELTA, it actually comes after AdaDELTA. AdaDELTAs come actually quite the same years, right? AdaDELTA, the adaptive learning rate method here, used the similar concepts, but it has this delta x to use as the enhancement of the weight, while the IMS prop use just the accumulation of gradient to divide here. Okay. Yeah, and this is the IMS prop. What is the difference between IMS prop and AdaGrad? You might wonder. Right? Let's go back to AdaGrad. In the AdaGrad, you have the accumulated of the square gradient. The accumulation would use since the beginning point. Let me change the battery of my camera for a moment. I'm still waiting for the DC coupler battery to use with this camera. Otherwise, I still have to switch this small battery once in a while. Okay. Let's continue. Right. So this is AdaGrad. Compare this AdaGrad to the RMS prop, you will see that the difference is only in terms of the accumulated square gradient. That is, instead of taking the accumulated square gradient since the beginning, it takes the accumulated square gradient just before that point. So if you compare RMS prop to AdaDELTA, well, AdaDELTA might be better here in terms of optimization because it introduced the change in parameters in terms of the advancement of the algorithm though. But the RMS prop has further modifications. That's the catch. Further modification of the RMS prop, because if you take a look, we'll take a look at the function later. RMS prop in the proposal, it also has this modification together with the Nesterov momentum. So instead of having just an adjustment to the parameters alone, it also includes the Nesterov momentum. That is, instead of using the current gradient to update, you can look ahead and use the gradient of the next step to update the current answers. Let's take a look at the algorithm. Right. Starting from the beginning again, get the mini batch, and then first apply the interim update to get the theta tilde here, and then use this theta tilde to estimate gradient, look ahead, estimate gradient over there, and then use that estimated gradient to perform accumulation. And then you can see that here it update only just using rho as the decay rate to specify whether you want to use a lot of previous value or just the current value. And then use this R to compute to update the velocity. Okay, use this R to update the velocity by adjust the learning rate and then multiply with gradient, and then use that to update velocity. Use the velocity to update the parameters. This is RMS prop with Nesterov momentum. Okay, the same concept as Nesterov momentum with SGD. Take a look at the next step. Estimate the gradient of the next step. Used to update the current location, the current solution. This is the same thing, right? But rather than doing that alone, it also doing what RMS prop does, which is to uh, have the accumulated gradient to weight the learning rate. Okay, let's take a look at the function. This one is RMS prop here. Right, so RMS prop has the learning rate specification, the rho, and momentum here in case you want to use momentum, and epsilon. Epsilon is a small value used to make sure that it doesn't hit 0. And there's here center as well. Gradient anomalized by estimated variance of gradient. So there's the here to use the variance of gradient to center the gradient, but well, since I did not mention it, think about this as the scaling of the gradient, that it kind of trying to scale it down. So this would introduce the normalization of the gradient a bit. Maybe you can take a look at the introduction of the center parameter here later on. But for now, you can see that you can introduce the momentum in as well for this one, for RMS prop. Then in 2014, Kingma and Barr has introduced another adaptive learning rate optimization called ADAM, okay, derived from adaptive moments. Okay, this one is quite popular with the current implementation of Keras. The ADAM, comparing to the RMS prop, you can think of it as RMS prop with momentum. But wait, didn't we just talk about RMS prop with Nesterov momentum? Yes, but there are certain difference in the ADAM algorithm. Let's take a look how does that differ. First, ADAM momentum is incorporated directly to estimate the first order moment. It used the moment as well. And then second, ADAM used the bias correction to estimate from the initialization. What does it mean in algorithm in terms of the bias correction? Let's take a look at the calculation in the pseudocodes, then you might get a better idea. Okay, so in terms of learning of the parameters, ADAM is considered to be one of the best right now, and actually there's the Nesterov ADAM as well if you want to use the next step to update the current step. Okay, let's take a look at ADAM. Here, first start with the step size or learning rate, the epsilon, and we have this exponential decay rate for the moment, P1, the row 1 and row 2. Okay, this is 0.9, 0.99, the decay of the moments. We'll see later on what does that mean. And a small constant for stabilize the calculation so that there's no divide by 0. So initially, first and second moments will need to be derived and will need to be set to 0 for both, right? Well, think about them as the accumulated gradient. Actually, they are quite the same as the accumulated gradient. You see that in the algorithm later on, right? And the time step here equals 0. And then for each of that, you need to sampling the mini batch and then calculate gradient. Okay, the gradient of the current position. Once you get the gradient, then you can increase the time step to t+1. And then you update the bias first moment estimate S with the gradient and the bias of second moment with the gradient square. Right, gradient and gradient square. What is the difference? First moment of gradient would incorporate the direction plus and minus sign into it as well, while the second moment would take into account only the size of change so far. Okay, then we would have this correct bias of the first moment and correct bias of the second moment, which is S and R here, and then divided by 1 minus rho, 1 minus rho, and this is also 1 minus rho 2. Okay. And then next, then we use S and R here to update using the first moment and the second moment to update as the gradient. Okay, as gradient to update the parameters. Now let's consider this a bit. S hat is actually gradient, right? S hat is actually gradient, the momentum, because you just multiply 1 minus rho here, divide 1 minus rho, and this is the multiply with 1 minus rho. So basically this is a gradient. And 1 over r squared is the accumulation of gradient. How does this differ from, say, AdaGrad? Can you notice the difference? Do you notice the difference between these ones and AdaGrad? And RMS prop. Well, maybe AdaGrad is quite too far away. Compare this one to RMS prop, the one that we just saw here, to this one. What is the difference between RMS prop, which use the accumulated gradient to weight the gradient, with this one, with Adam? What are the difference? The difference is in terms of the, you can see here that Adam momentum is incorporated directly to the estimate of the first order of moment. That means that in the first order, this is the momentum, right? Yeah, it's the momentum, right? Because you take the previous value and then take part from the current gradient. So this is the momentum, has already been incorporated through the first moment. In the second moment, Adam include the bias correction to estimate to account for the initialization of the origin. That's that mean. Okay. So here we have the first moment where which take part, which we have 1 minus rho to multiply with g. When you divide with also 1 minus rho here, you kind of making the correction of this initial assumption of rho 1 and rho 2 to the moment, so that the scale here, because you take a look here, you at the end you need to calculate the division between the first moment and the second moment. And because if you take a look at the rho 1 and rho 2, if we take the value of rho 1 to be 0.9 and the value of rho 2 to be 0.999, that means 1 minus rho 1 is essentially 0.1 and 1 minus rho 2 here would be 0.001. Okay, when you make a division like this one, this would be in the scale of 1 over 10. This will be the scale of 10. This will be the scale of 1000. This part. This will be the scale of 10. This one will be the scale of 1000. And when you put it here, this would act as the 1000 will scale to about 100 something in the division here, and that would make what? That would make the value here reflect to the gradient value in this one. And for the r hat here, this would reflect to the size of the gradient so far as well. But now you have two parameters that could control the change here. You have the decay rate for the moment, and you have the decay rate of the accumulated gradient. With these two, you can control the different rate of gradient, whether you want to use a lot of existing values of the gradient and the accumulated gradient, or with a lesser value of them. Okay, so if I were to compare Adam, I would compare that this one is very similar to the AdaDELTA, right? But AdaDELTA use the change in parameters directly. For this one, it is quite like Prop, similar to Prop, but with the ability to control not just in Prop, you have an ability to control the rate of accumulated gradient, but you don't have the ability to control the decay of the gradient itself. Why for this one, right? Why for that? Why for this? Right? For this, it has the gradient incorporated into. It has the momentum, which is in the algorithm. If you compare this one to the Nesterov IMS prop with Nesterov, you will see that now you have gradient here in momentum as well. Well, the problem is that this momentum doesn't it's very strictly toward the Nesterov criteria. It is not like normal IMS prop with momentum. You see that they are quite similar to one another, right? But this one, well, is IMS prop with looking at the next step, not with the just momentum. Well, you have IMS prop with momentum with Adam here. All right. Okay. Adam can also has the Nesterov version, looking ahead version of Adam. Okay, and it is described in the paper, the incorporating Nesterov momentum into Adam in the paper in 2016 by Dorset. Let's take a look at this first. Here, this is called Nada. Okay, we have this Adam. In Adam, you can specify the learning rate. Beta 1 and beta 2 is actually the row 1 and row 2, same thing here. And there is the condition called AMS grad. AMS grad is whether you want to evaluate AMS grad variant from the paper on the convergence of Adam and beyond, which default is false. I will recommend you to read the paper. I will not cover it here, as it a part of the derivation of the original algorithm here. Otherwise, there will be like lots to cover, which I don't think I can do them all. Now, Nada, right? Nesterov accelerated Adam. Okay. This is again algorithm from the paper, not from the book, which make this a little bit more confusing when you want to understand them. Right, let's see. So here you have the first and the second moment vectors, right? M0 and N0, which you have to use later on. And then for each step, we have like we have to calculate gradient, okay, GT, gradient at time t, which is from the delta of the function that we have that we have the loss function, and then the gradient will be used to add to the first moment and the second moment, right? The same as in Adam, okay? And the Nesterov condition is applied down here. That is for M. M is used to M is then it is corrected with to be M hat and N to be N hat. right? Instead of so m is calculated from mu t, right, over 1 minus sum of the mu I of the previous step. These are the hyperparameters, the alpha and the mu. And for this one as well, using 1 minus mu t of the g, and then accumulation of the previous mu. The mu here are the parameters that you need to specify on the path of the optimization. These are the parameters that I used to update here, both new here for the moment and for the second moment and for the first moment. So they are quite the same as the value here, exponential decay rate for this one. And then for n as well, n is corrected by 1 minus newt, and then both are divided, right? And then apply to the theta t. Okay, this is the Nesterov accelerated adaptive moment estimation. Okay, so we use the we calculate this gradient of the previous iteration delta, right, using previous iteration delta to calculate the whole thing here. I would recommend you to read the paper here. Now let's take a look at the function of Nadam. Where is it? Nadam. Right, Nadam also has this beta 1 and beta 2, just like in Adam. Adam is Iris-Pop with momentum. Nadam is Nesterov with momentum. So it's from this paper. Here, incorporating Nesterov momentum to Adam. This is Adam. This is AdaGrad. And you can see that AdaGrad used the accumulated gradient and then divide that. For Adam, Adam used the moment, the first and second moment, and then calculate the change by the division of the first and second moment. For the Nesterov accelerated adaptive moment, let me find the I did copy. Huh. Let's look at this one. Somehow there's a fix in the algorithm here, which make it differ from what I had in this paper. Okay. Instead of my version, let's look at this one. Somehow different. Two times open the same file. All right. So here we need to calculate the gradient, and then this is the normalization of the gradient with the parameters mu, and calculate the first moment. The same thing actually, and the adjustment of the moment. Okay. The same thing so far. This is the Nesterov. This is the second moment, adjustment of second moment, and the momentum. Okay, this is the momentum part of the gradient, and then we use the momentum part of the gradient. We use the momentum part of the gradient, and then instead of the first moment. Okay, mine. Yeah, I did take it from this one, which doesn't contain momentum. It contains momentum here. Sorry. It is already correct. Right. So it's just rearranging of the equation that make it confusing. So here I draw it from the paper in the ICLR. This one is the one that is posted on the Stanford project, which make it a little bit different in terms of the rearrangement of the equation, but they are essentially the same. That is, this is the momentum part, the mt minus 1 plus gt, the momentum of the gradient. So instead, this is incorporated into the adaptive moment. About Nesterov, in order to be Nesterov, it needs to evaluate the Nesterov condition of the next step, but somehow I don't see that here. Let me check. Nesterov accelerated adaptive moment. That means we need to take the next step. Right. So the Nesterov accelerated adaptive moment is Adam with the not the Nesterov condition, but the Nesterov acceleration in terms of the gradient value here. So we have the hyperparameters that would control the learning rate here, alpha, which is like the values that control the change in the parameters, and we have this the new value, the second moment, which accumulate the size. You can see here, accumulate the size of the gradient square so far, and we use moment to combine this in the first moment. But we also have the adjustment of moment according to the gradient change previously, okay, into the M, and this is the incorporation of the Nesterov momentum into the adaptive moment. Right. So we have the GT here to indicate the moment, and use that to add to the momentum here as well. In the Adam, we have the first moment S, but this is from the gradient of this. But that is something like the moment of the momentum of the moment here in the incorporation of the Nesterov condition. This is the mu t plus 1. The future step specify. Right. So now if we compare the algorithm according to the original one without Nesterov condition, with from SGD to the one SGD with momentum, this is Nesterov accelerated gradient, and the AdaGrad and AdaDELTA and Nesterov. Take a look at how it reached they are finally reached the solution, but you can see that SGD is quite slow. While momentum allow you to carry on to a different path, but it reached the location quite fast. Focus on the green line here. But when you compare it to the adaptive moment perform better when it comes to the convergence to the solution, right? This is AdaGrad is still slower than the rest, but AdaDELTA is quite fast. Nesterov is okay because it's quite similar to AdaDELTA. AdaDELTA takes a previous step in consideration. Nesterov accelerated gradient jump just like the momentum because this is also momentum-based optimization. It kind of jump past the point and then finally reach the location. So that's why that make this AdaDELTA and the Adam quite popular. Comparing for all of the performance of a different method here, you can see that SGD in terms of the convergence of the mean square error is actually slower than the rest. Adam is quite good here. Nadam is even lower, a bit lower with the a lot faster convergence here. For Nesterov is very similar to Adam. Okay, but there's no AdaDELTA AdaGrad in this paper comparing the performance. So when you although this results tells you that this is from the book from the use of different algorithm on the digit classification. But if the task is different, you need to choose. There's no consensus at this point. It's still on debate. And actually, there is even a paper coming out claiming that no matter what algorithm that you use, actually doesn't matter. They are quite similar. The performance is very similar to one another. The solutions are also very similar to one another. And actually, the one that's claimed to be better is only for some situation. In some situation, that it is actually worse. So let's say that the most popular technique that has been used already covered in the Keras library and also in PyTorch library. There are these SGD momentum, Nesterov with momentum, AdaDELTA, Adam. These are the popular one. But the choice of which algorithm to be used when you use it in your work depends on the trial. So you have, up to this point, you may see how different algorithms work. You should know which one converges faster than which. You can try out and then reason on the results that you got in the optimization of your work. This is all of the lectures today, and you can see that all this theory has been incorporated into the. Oops! Did I switch back to the slide? I don't remember. No. Well, no one tell me. All right, sorry. Should I? Okay. So what I have been talking about so far is this. I got to switch the slide. Here is the animation of the convergence of different optimization technique. From this one, you can see that SGD is very slow, right? RMS, prop and AdaDELTAs are quite fast and can converge to the proper optimum solution. While for the momentum-based technique, like SGD with momentum and Nesterov with SGD, kind of jump past through the point. But well, that might be because of the nature of stochastic, maybe because of the nature of momentum itself, that alone it kind of carry you off, having a lot of exploration to go on. While for the AdaGrad and AdaDELTA, take into account of the different steps that you need to take. That is, you need to take like a large step at the beginning and then smaller one later on. AdaDELTA take into account of the parameters as well, the change of the parameters, and RMS prop. RMS prop also converge on the same path as AdaDELTA because they are quite similar to one another. Right, this is what I have been talking about, and in terms of performance, it depends on the task. One of the work in the digit classification show that NADAM is better than the others because that work is proposal of NADAM. But when you take a look at different papers, you see that they are quite the same. Actually, there might be no difference at all in terms of the solution that you get at the end. Okay. So in terms of the choice of the optimizer to choose, there is still no consensus which one is better than which. That's why I mentioned that there is a research work that actually claim that the technique like NADAM, like ADAM, that claim to be better. In some case, RMS prop is actually better. That depends on the task at hand. So I would say that you need to try them out in order to know which one would work for your work. Well, because these sometimes depends on the difficulties of the problem itself and the complications in the data that you have. So up to this point, depends on which one you are familiar with and which one will give you the best in terms of tuning of parameters. Right. So this is all of the lecture today. There seems to be questions here. Could you please share the link to the Facebook group? Okay. The link to the Facebook group. You mean share it here, right? The links of materials in class. Are you referring to the Keras website? Materials, if the materials you mean the that article, it's actually in this site as well. So maybe I'll just go here. Here is the link. And for the article, you can actually just go into, actually I should send to everyone because I'm talking here to everyone. So let me here. So these are the links to the optimizer API reference and the paper about, I think it's the Nesterov, the NADAM. Right, Nesterov momentum with ADAM. Okay, this one is not the published version. It's more like the manual version, the report version of the work. The published version is referenced in the published version is referenced in the lecture in this slide. If you want this one, just search in Google. You will find from ICLR 2016. Okay. Well, and this is all of today's lectures on the optimization of the of deep learning model. You can see that a lot of these are related to the specification in the compilation, the method that you need to specify in the model so that the solution will be reached. Although they are quite detailed, these techniques usually affect mostly the performance of the optimization. Okay, there are attempts right now to apply more of the stochastic technique that will allow a lot more exploration to the solution. However, doing so increase the computation time exponentially. So there's the trends in the research that try to combine higher computation, the high performance computation algorithm with the one that we have here. You can see that the technique that described it in these lectures are very, I would say they are very straightforward, because it's either you use gradient to update, you use the momentum of the gradient to update, you use the momentum by looking at the next position to update, or you use the accumulation and then use them to weight your update. There are plenty that can be still improved from here. Like you can have like multiple choice update, multiple solution update, right? So this is still a hot topic in research. If you are considering doing maybe your further study in deep learning, maybe in terms of the architecture itself, these would be a very interesting topics to consider on. But they are quite algorithm oriented rather than the application of deep learning that we have seen in a lot of Facebook shares nowadays, right? All right, and okay, next time if I were to forget to change the screen, please tell me. I did not have another screen showing up. Maybe I should do that. I forgot to do that, so that I would know the current whether it's still, well, whether it's on which slide. Right, this is quite embarrassing this time, right? Any questions about the content in this lecture? Or do you have maybe you have ideas on further enhancement of the optimization? You can share. We'll see whether it's like making sense, or maybe you can have a better algorithm to update parameters, a better strategy to update parameters faster, still get the correct results. And that would be nice. I'm thinking like maybe you can have something like ABC algorithm that you have a B to direct the moment and then update the direction of gradient according to those. Yeah, maybe that would make sense. Yes, there is no assignment for this week. We will have assignment on the next week. All right. If there's no questions, let's call it a night and see you next time. Right? Next time it will be on convolutional neural network, and there is another assignment on the way next time as well. It will be on basic image classification. So let's take a look at that next time. If you have questions about the technique, about the model, about a paper, please ask in the Facebook group. I will answer your questions once I saw the post. All right. Right. We have a question here. Right. Your friend asks in XOR feed-forward network. There seems to be we need to have backpropagation to optimize cost function, right? Yes, you need to do that. So this will be a simple backpropagation with just 2 input. All right. No questions? You can ask on any part of this lecture. But well, when you for the whole lecture here, um, you can see that the whole thing is about learning rate. Whether you you would like to have a constant learning rate, the learning rate that changed by momentum, the learning rate that changed according to the adaptive, right? That change according to the accumulation, the learning rate that change according to the moment, first and second moments, right? So still they are all about learning rate, but you can see that different learning rate adjustment give you the solution to the convergence solution with different speed. When you lecture 5 to 7 record available, 5, 6, 7, right, including this time. Well, that's my homework. Say, I'll try to make it within this week. I'll have to kind of edit it a bit and encode it and submit to the YouTube. Promise this week, for sure. All right. Okay, I will hand out the previous assignment grade including this one. For the first one, I almost done. Now it's like I'm grading that up to about, I would say about 70% on the way. I will hand it out on the grade of the previous assignments. If you do all the steps on the way, then you will probably get the full score. Only the score will be deducted if you did not complete part of the requirement. But well, I will hand out the grade later on. All right. Any more questions? Okay, so then see you next week. I will try to post everything within a few days. We should take, well, for each lecture it take about an hour to encode, but it take about 2 hours to edit. I will try to finish that homework as soon as possible. Once I got them, they should be faster, I suppose. And well, the question about the lecture, any auto factors that we should look up to when the weight stuck at the local optimum. In that sense, if your weight stuck at the local optimum, the revision of the model shouldn't be toward the optimizers. When would you want to choose the optimizer? When you want your solution to converge faster, right? But if your network, if the deep learning network that you have kind of stuck at the local optimum, what would you do? Instead of looking at optimizer, you should think about the regularization. Okay, you need to find a better way to regularize your network, right? Just like in the last lecture, how to regularize your network. First, you can have to do something like data augmentation, right? You can adjust the criteria, that's for sure, for the parameters. Put in the dropout, include something like data augmentation for image, like you can rotate the image around, you can crop the image doing the file transform, you can do the what is called the adversarial training to increase the comparison. You can regularize the network by doing the multi-head, multitask network. That it let your network perform different tasks at the same time. Actually, next time you will see a version of architecture called convolutional neural network, which relies on the share of parameters to regularize the network, the pattern matching. So it kind of match pattern better in that way because it share the parameters in the computation. Okay? Because the same small mass is used to compute the feature maps for the whole image. So that is how you regularize network. Should answer your question about if the weight start at local optimum. The answer is not on the optimizer, but it will be on the architecture of the model. Okay. And there are other modification of the architecture as well, like using attention to just focus on small part, right? To reduce the data rate, or using something like embedding, right? To convert the data from the multiple variable to just the latent variable in the sequence recognition. Okay, so those are the architectural adjustment that could allow you to avoid local optimum, which we'll take a look at them as well. Part of them that are in those architectures. Okay, local optimum, which we'll take a look at them as well. Part of them that are in those architectures. Okay, right. So at least, I promise you at least one would go out tonight for lecture 5, right? And and I will try to complete all of this in the pipeline as soon as possible. Should be within this week. Right. Okay. So let's call it the end. See you next time. Next time it will be on CNN, convolutional neural networks. So that means we will also run the lab in the lecture as well. So I will share the notebook to you guys so that you can run together with me here. Okay. All right. See you next time.